Hello friends, today we are going to see the operations on an AVL tree. An AVL tree is a binary search tree in which for every node the allowed balance factor is -1, 0 and +1. Any balance factor below -1 and more than +1 is not allowed in AVL tree. If you don't know what is balance factor, then you see my previous video on AVL tree and the need for AVL tree. The link for that video is mentioned in the description below. So let's go ahead for the operations. The baseline is that you have to calculate balance factor for every node in this binary search tree and then decide whether this binary search tree is AVL tree or not. And if this binary search tree is not the AVL tree, then we will convert this into AVL tree by performing some operations. Those operations called as rotations. So let's see what is that. For 10, what is the balance factor? See, the left branch height is 2 and the right branch height is 3. So 2 minus 3 is -1. Then for 8, 1 minus 1 is 0. Then for 7, 0 minus 0 is 0. For 9, 0 minus 0 is 0. See, there is nothing means there is null for these nodes. Now for 15, 1 minus 2. So 1 minus 2 is -1. Then 1 minus 1 is 0 for 17. For 12, 0 minus 0 is 0. There is nothing for 12. Then for 16 it is 0 and 18 also it is 0. So these are the balance factors. See here, every node balance factor is in -1, 0 and +1. So this binary search tree is an AVL tree. Now let's perform the insertion operation. Let's insert some nodes. Okay, so suppose you want to insert node 6, means you want to insert element 6 inside this binary search tree. So 6 is less than 10, less than 8 and less than 7. So that will be on the left side of 7. Okay, so let's see the changed balance factors. For 10 it is 3 minus 3, so 0. And for 8 it is 2 minus 1, so 1. Then for 7 it is 1 minus 0, so it is 1. And for 6 the balance factor is 0 minus 0, that is 0. See, even if we have inserted an extra element 6 in this binary search tree, this binary search tree still remains AVL tree because it satisfies the property. Now let's insert 4 inside this binary search tree. See, 4 is less than 10, less than 8, less than 7 and less than 6. Okay, let's see the changed balance factors here. So 1, 2, 3, 4. 4 minus 3, so 1. Height of left subtree minus height of right subtree. Then for 8 the left subtree is 3 and right subtree height is 1. So 3 minus 1, that is 2. Then for 7, 2 minus 0, so that is 2. And for 6 that is 1 minus 0, so that is 1. And for 4 it is 0 minus 0, so 0. Okay, now you can see after inserting 4, 2 nodes are imbalanced. Okay, that is this node 7 and 8. These nodes are now imbalanced and this binary search tree is not AVL tree now. We have to convert this binary search tree into AVL tree. Okay, now how to do that? First you have to go from the leaf node. Okay, so 0, yes, it is allowed. Then 1, it is allowed. The balance factor 1 is allowed. Then balance factor 2, yes, this is not allowed. So you have to do some operation to make this branch balanced. Okay, so see here now, this imbalance is caused because of these two branches. Okay, now for this node 7, 6 is the left branch, again 4 is the left branch. Okay, so this is a L type of imbalance, we can say that. Okay, now we have to perform the LL rotation to make this branch balanced. So as this is a skewed branch, then you have to make this branch as the balanced branch. So you can imagine, if there is a branch in this way, that is C, A and B, this is a sub branch in this binary tree. If there is a branch in this way, this means that B is less than A is less than C. Because of the binary search tree property, obviously B should be less than A and A should be less than C, because A is the left child of C and B is the left child of A. So when we see at this property, we come to know that we can write such a branch in which B is less than A and A is less than C in some other way. So that way is, take A in the middle as the root of that subtree, B as the left child because B is less than A, and C is the right child. Okay, so what happens in this way is that the balance factor of all the nodes remain 0 here, means they become balanced. In this subtree all the nodes are balanced. So see here, 7, 6 and 4. So 4 is less than 6 and 6 is less than 7. So you can make this as 6 as the root, left child is 4 and right child is 7. Okay, and you can attach this branch to the parent of the imbalanced node. What is the imbalanced node? From where the imbalanced starts? So this is the imbalanced branch and the node is this 7. So just replace this branch with our new balanced subtree. Okay, so this is the balanced subtree. So 6, 4 and 7. Let's see the balance factors now. So the balance factors are here. See, for this it is 0, for this the balance factor is 0 because there is nothing on the left child and right child. So for 6, 1 minus 1, so that is 0. For 8, see, 2 minus 1, so that is 1. And for 10, see here, 3 minus 3, so that will become 0. So now all the nodes in this binary search tree satisfy the property of AVL tree. So now this can be called as the AVL tree. So now there is another method which is explained all over the internet as the method for LL rotation or any rotation. I will explain you that method. So first I will make previous situation. So this was the previous situation. Now in this situation the balance factors were different. So they were 0, 1, 2, 3 minus 1, 2 and this is 4 minus 3. So that was 1. These were the balance factors. So now because of the balance factor 2, This was not satisfying the AVL tree condition. So the method is that if this is your unbalanced branch CAB, okay, now you have to just imagine pulling the middle node. You have to pull the middle node. So just pull this node A. So you can now imagine if you pull A, then B will be on one side and C will be on the other side. I will write, after pulling A, B is on one side and C is on other side. Just imagine in this way. If you pull A goes in the middle, B on one side and C on other side. So this is the subtree. Converted means this is the balanced branch now. You can say as subtree. So this is the way which is explained on internet. So the reason behind I explained you this value method, which is watching the greater than less than values and then directly writing them in the subtree as the balanced. So the reason is that when you follow this pulling method, you follow this blindly. You don't know the reason why you are pulling this middle node and why this node is on the left side and this node is on the right side. So the reason behind pulling the middle node is the same reason as I have explained of the values, this sorted values. So now you know the reason also and you know the method also. In some complicated cases, always this value method proves to be easy, and in some more complex cases you have to combine these two methods like value method and the pulling the middle node method. So now let's go to the next rotation, that is RR rotation. The RR rotation now, that is the right imbalance. Now this is the binary search tree and this is also an AVL tree because each node of this binary search tree satisfies the condition of AVL tree. Now let's insert a node. So first suppose insert element 18. So 18 is greater than 10, greater than 15, greater than 17. So 18 inserted. Now let's check the balance factors. So for 17 the balance factor will be 0 minus 1, so that will be minus 1. For 15 it will be 1 minus 2, so that will be minus 1 again, and for 10 it will be 2 minus 3, so that will also be minus 1. So these are the new balance factors, and for 18 it is 0. Now by watching these new balance factors, we can say that this is still an AVL tree because the balance factors satisfies the AVL tree condition. Now let's insert another node, that is 19. So 19 will come at the right of 18 because 19 is greater than 10, 15, 17, 18. So the 19 place is here. Now let's check the balance factors. For 0 balance factor is 0. For 18 it will be minus 1. For 17 it will be minus 2. For 15 it will be 1 minus 3, so minus 2. And for 10 it will be 2 minus 4, so it will be minus 2. Okay. Now you can see as the balance factor is minus 2 here, so the AVL tree condition is not satisfied. Now we have to perform some rotations to convert this binary search tree into AVL tree. So now go from the leaf. So for 19 balance factor is 0, so it is balanced. For 18 the balance factor is minus 1, so that is balanced. For 17 the balance factor is minus 2, means it is less than minus 1, so it is not in the set minus 1, 0 or plus 1, so this is not balanced. So you have to go looking at its right branch now here. So why this has been imbalanced, you have to see that. So when we check that, we can see there is a right branch for it, because of which 0 minus 2 has become into a balance factor of minus 2 for this node. So here this skewed branch we have to balance it. So for this skewed branch I will write it like C, then A and B. Okay. Now in this you know that 17 is less than 18 less than 19. 17 less than 18 less than 19. That means C is less than A less than B. Okay. Now obviously you can take A in the middle. As C is less than A, you can take it as the left child and B as the right child. Okay. Now so directly you can take 18 in the middle, 17 as its left child and 19 as its right child. So I will show you how will it look after balancing. 18 you have to attach to the parent of the imbalanced node, that is 17. So 18, 17 is its left child and 19 is its right child. Okay. So this is the way we balanced this skewed branch. Now check the balance factors. See here 2 minus 3. So it will be minus 1. Again for 14 see 1 minus 2. So that will be minus 1. And for this it is 0, 0 and 0. So in this way we have balanced this binary tree. Now it can be called as AVL tree. You know the another trick, just by looking at the image you can do that. Actually this is an easy method and the pulling the operations will be somewhat difficult in complex cases, but in this case the pulling operation method is easy. Now suppose you pull A, then C comes on one side and B comes on the other. So that will be like A, C and B, because you have pulled A. So previously here it was 17, 18 and 19. Now pull A. When you pull A, you will get it like, when you pull A and attach it to 15, means the right child of 15. So 18 here, 17 here and 19. So this is the way we have balanced this binary search tree, and now this can be called as AVL tree. Now let's look at the next rotation, that is LR. So let's see the LR operation now, that is the left right rotation. Okay. Now see here, this is the binary search tree which is also an AVL tree. Now insert element 2 in this binary search tree. So 2 is less than 10, less than 7, less than 4. Okay. Check the balance factors. For 2 the balance factor is 0. For 4 it is 1 minus 0. So that is 1. 2 minus 1. So for 7 it is 1. For 10 it is 3 minus 2. So that is 1. Okay. Still this is an AVL tree because the balance factors are in minus 1, 0 or plus 1. Now let's insert 3 in this binary search tree. So insert 3. Okay. So 3 is less than 10, less than 7, less than 4 but greater than 2. Okay. Now let's check the balance factors. For 3 the balance factor is 0. For 2 it is 0 minus 1, so that is minus 1. For 4 it is 2 minus 0, so that is 2. For 7 it is 3 minus 1, so that is 2. And for 10 it is 4 minus 2, so that is 2. Okay, now as 2 is the balance factor for some nodes here, this is not an AVL tree now. We have to perform some operations and convert it into the AVL tree. As I have told you, you have to start from the node. The first imbalancing node is the node with value 4. Okay, the balance factor is 2. So for this, see here L, so left branch, and then there is a right branch. Due to these two branches, the balance factor of this node has become 2. So this is the imbalance, that is LR. Now we have to perform some rotation to make this balanced. So first we will follow the method of less than and greater than. I will show you. See here, how is the case? That is C, then A and B. This is such a case. Okay, so now sort CAB. So see here, what is C? C is 4, then A is 2 and B is 3, the values. Okay, let's sort them. So that is A, then B and C. Okay, this is the sorting in this branch. So simple thing, take B in the middle. As A is less than B, take it to the left, and C, take it to the right. This is the simple thing, and attach B here. So what is B? That is 3. 2 is less than 3 and 4 is greater than 3. Okay, now you check the balance factors. So that is 0, 0, 0. 2 minus 1 is 1. 3 minus 2 is 1. Now this is an AVL tree and the tree is balanced now. So this is one method. You may find this method as simple. Now we will see another two-step method which some people may find it as easy. So I will write that method. See here, first it was 4, 2. So this was the case. Now as this is an imbalance, here the balance factor is 2 and 2, and for this also it is 2. This is minus 1 and this is 0. So this was the situation. Now consider this LR as two-step process. I'll just clean it. So that is C, A and B. Okay, so the LR rotation will be split into two steps. The first step is C, then it is A, this is L. Now the first step is, consider this as RR. Just imagine this. Okay, so RR. Okay, just imagine there is a node here. Just hypothetically consider that there is a node there. So if it is a RR case, then what will we do? We will take B in the middle, we will pull B and A will be on one side and this imaginary node will be on the other side. That is the simple thing. So what will be the answer for that? C. I will just write C here first. Okay, now if we have pulled B, so A will come on one side, imaginary node on the other side, and B will be attached to parent of A. So that will be like this, see, B and A, and here that imaginary node. Okay, now this is a LL case. Just leave this imaginary node, forget this hypothetical node. The second step is LL, means this LR is divided into two steps, that is RR first. When RR is solved, then we check for LL. Okay, now if this is LL, pull here, so that will be B in the middle, C on the other side, and A on the left side. So when we pulled it, it will become B in the middle, A on one side. See, if you pull it here, imagine A will go on that side, A will go on this side. So, and C on this side. So here A is 2 and C is 4 and B is 3. Okay, so the condition is now like this: B, left side is A and C. So that means it is 3, left side is A, that is 2, and right side is C, that is 4. Okay, so 3, 2, 4. Just attach it to the parent of the imbalanced node, that is 7 here. So now let's attach 3, 2 and 4. So now the tree will be balanced because it is 0, 0, 0, 0, 1 and 1. So let's see the RL rotation now. RL is for right left imbalance. Okay, now this is the binary search tree, and this is an AVL tree also because it satisfies the conditions for AVL tree. Now insert 18. Insert 18 first. So see, 18 is greater than 10, greater than 15, greater than 16. So 18 will come here. Now check the balance factors. For 16 it will be -1. For 15 also it will be -1. Then for 10 also it will be -1. Okay. Now see, insert 17 now. Okay, 17 is greater than 10, greater than 15, greater than 16, but less than 18. Okay, so that will be the left child of 18. So now see, the balance factors have changed. So for 18 the balance factor will be 1, 1 minus 0. For 16 it will be 0 minus 2, so that is -2. For 15 it is 1 minus 3, so that is -2, and for 10 it is 2 minus 4, so that will also be -2. Now this is not an AVL tree because the balance factor -2 is not in this set, it is less than -1. So now it is not an AVL tree. So the first method, just sort these numbers. So I will write them here. C, then A and B. This is the structure, and 16, 18, 17. So see here, C is 16, then A is 18 and B is 17. Okay, so sort them, it will come like 16, 17 and 18. So C is less than B, is less than A. Convert this into a tree. So B is the node, means B is the root, C on the left side and A on the right side. Okay, so this is a balanced branch now. So write that balanced branch here and attach it to the parent of the imbalance node. So it will be like, see, B is 17, so it is 17, C is 16 and A is 18. There is no need of writing all this also. You can just directly take the numbers here, sort them, write the middle number at the place of the imbalance node, to the left the lesser value and to the right the greater value. So in this way now we have balanced the tree. Let's check. The balance factor is 0 for 18, then 0 for 16, 0 for 17, for 15 1 minus 2, so minus 1, and for 10 2 minus 3, so minus 1. Now this is an AVL tree. Now let's go to the second method. So the second method is a two-step method. I will show you. For that I will write it as it was previously. So it was 16, then 18, 17. Okay, and balance factors were minus 2, minus 2, minus 2, minus plus 1 and 0. Okay, so this was the previous situation. Now see here, this is a right left imbalance, RL. Okay, RL imbalance. So for this RL imbalance we will divide it into two steps. First will be LL. Just imagine a node here to the left of B. So this is LL. So for LL rotation, as you know, you have to pull B. So pull B. So imaginary node will be on left side and A will go on right side. So I will write here. So after pulling B, what will be the situation? C is the first node and to its right the situation is B will be attached. So B, right, left and right. So to the left this is an imaginary node and to the right there will be A. Okay, C. Now C, B and A. So this is a right thing. Right. So we have to now forget this imaginary node and we have to apply RR rotation. For applying RR rotation you have to pull the node, as you know. So pull the node or use greater than less than method, means just sort the values and directly put the values as a binary search tree and connect that branch to its parent, to the parent of the imbalance node. So if we pull B, so C will come on one side, for B will be the root, C will come on one side and A will be on the right side. So C on the left side, A on the right side, and B is in the middle, that is the root for that subtree. So we have pulled B. Now obviously BCA, just write that balanced branch here at the place of the imbalance node. So B is 17, see, then less than 17 what is there, 16, and greater than 17 is 18. Okay, so now again this tree is balanced. 2 minus 3 is minus 1, 1 minus 2 is minus 1, 0, 0, 0. Now this is an AVL tree. So this is how we perform these 4 rotations. One complex example is here. So see, this is a binary search tree and let's write the balance factors. Now the imbalance node we have to check from the leaves. So we went up. Now yes, we found the imbalance node as 15. So this is a totally inner node. So the leaves are not going to be involved in the rotations now. So how should we do it? See here, for 15 the imbalance is because of this branch. Okay, so that is R imbalance. Okay, now 18 is the middle node for RR, so we have to pull this node. Okay, just imagine you are pulling 18. So when you pull 18, obviously 15 will go on left side of 18 and 20 will be on right side of 18. Imagine this whole thing as C, A as 18 and the whole right branch as B. So if you see, this is the status here. So pull A, so A will be in the middle, C and B. So that is what is done here. See here, we have pulled 18, so 18 has come in the middle, and this is C and this is B. Okay, and this is A. That is simple. Okay, but there is a big question here. What about 16? 16 was the left node of 18, the left child of 18. Now where should we put 16 here? What will happen of 16? So in this case we have to combine both methods, that is the greater than less than value method and the pulling method. Now we have already pulled, so we have used pulling method. Now we have to go for the value method. Just check the correct position of 16 in this. Okay, see here, 16 is less than 18 and greater than 15. So put 16 there. So 16 comes here. Mechanically, if you want to do it without watching the values, then a rule is that when you pull A, attach 16 as the right child of its parent, A's parent. So we have attached 16 to 15 as the right child. So in the upcoming video, in the next video, I will explain this with procedure in details. Hey friends, please subscribe to my channel as I post algorithm videos every day. And if you want a video on any particular topic, then please mention in the comment below. Thank you.